Hello, my dear students. In this lecture, let us solve some of the numerical on psychrometry without using psychrometric chart. Me, Dr. Shrikala from the Department of Mechanical Engineering, Global Academy of Technology. Now let's take up the first problem. This problem was asked in January 2018 VTU question paper. The atmospheric air at 101.325 kilopascal. So pressure is taken as 101.325 kilopascal has 30 degrees centigrade dry bulb temperature. So TDB as 30 degrees centigrade and 15 degrees centigrade dew point temperature. TDP as 15 degrees centigrade. Without using the psychrometric chart, using the property values, that means we are taking the values from the data handbook, we need to calculate the partial pressure of the air. It is taken as PA, water vapor, that is PV, specific humidity, omega, relative humidity, phi, the vapor density, rho v, and enthalpy of the moist air, HA. Now, to find this, first open the data handbook. In the data handbook, you have two tables, the table 1 and table 2. Table 1 gives the first column having the pressure and the second column having the saturation temperature. Whereas the table 2 gives the first column as TS or the temperature and second column as the pressure. So go to the second table, that is table 2, wherein you will have the first column as temperature. So there at T equals 30 degrees centigrade, find the pressure value. So pressure value is taken as, that is nothing but the saturated pressure, vapor pressure, which is taken as at 30 degrees centigrade, it is found to be 0.04214115 bar. And again next at temperature, dew point temperature TDP of 15 degrees centigrade, note down the partial pressure of the vapor PV as 0.017039 bar. But we know the total pressure will be equal to partial pressure of the air plus partial pressure of the vapor. So to find the partial pressure of the air, PA will be equal to total pressure minus vapor pressure. So we know the total pressure is, in terms of bar, it is 1.01325. That is atmospheric pressure minus vapor pressure, which we had noted down. So we'll get 99.62 kilopascal as the partial pressure of the air. So this is the first question which is asked. PA, that is partial pressure of the air, and PV, the partial pressure of the vapor. Next, go to the specific humidity. So specific humidity omega will be equal to, we know that the expression given as 0.622 PV by PA, that will be equal to 0.622 PV multiplied by PV is 1.7039 divided by PA, that is partial pressure of the air. It is 99.6211. So total specific humidity is 0.01064. So omega value we found out to be, that is specific humidity, so many this kg of the vapor per kg of the dry air. Next is relative humidity. So relative humidity phi will be equal to PV by PVS. So partial pressure of the vapor we found out to be 1.7039 divided by partial pressure of the vapor at saturation, that is 4.215, we'll get this relative humidity to be 40%. The next is vapor density. So vapor density equals mass of the vapor divided by volume of the vapor. So rho v is nothing but mass of the vapor by volume of the vapor. So considering the vapor as the ideal gas and it obeys the gas equation, so we have PV VV is equal to MV RV TV. So what is the partial pressure of the vapor multiplied by the volume of the vapor will be equal to mass of the vapor into the gas constant of the vapor gas constant and the temperature of the vapor. So to first let us find out the gas constant of the vapor. So that will be equal to universal gas constant R bar, that is given as 8.314 kilojoules per kg Kelvin divided by molecular weight of the water, that is H2O. So H2, that is 2 multiplied by H is 1 plus oxygen molecular weight is 16. So we'll get divided by 18. So RV is, we get it as 0.462. 0.462 kilojoules per kg Kelvin. You can also remember this value for solving further problems. Substituting this RV here, then cross multiplying MV by VV will be equal to PV divided by 0.462 TV. So M by V is nothing but mass by volume. It is nothing but the density. So density, vapor density will be equal to partial pressure of the vapor divided by RV into temperature of the vapor. So where TV is the dry bulb temperature. So please make sure it should be in Kelvin. So 273 plus 30 multiplied by RV, and in the numerator substitute the PV, we'll get the density of the vapor. Next, the enthalpy of the moist air, HA, will be equal to, we have to use this Carrier equation which says 1.005 TdB plus omega into 2500 plus 1.88 TdB. So in some of the books it will be TdB minus TdP, in some it will TdB, just TdB only. So I'm taking only this expression. So it is 1.005 into 30 plus 0.01068 into 2500 plus 1.8 into dry bulb temperature. So we get the enthalpy of the moist air. So HA is 57.45 kilojoules per kg of the dry air. We'll go to the next problem. It says the atmospheric air has a dry bulb temperature of 32 degrees centigrade and a wet bulb temperature of 26 degrees centigrade. In the first case, the relative humidity was given. Here in this case, dry bulb and the wet bulb temperatures are given. So determine the following properties for the given condition without using psychrometric chart. So first we need to find out the water pressure, partial pressure PV, specific humidity omega, dew point temperature, relative humidity phi, degree of saturation mu, and the density of the air in the mixture rho A, also density of the vapor rho V, enthalpy of the mixture H. So now let us solve this problem. Here the atmospheric pressure, as we all know, it is P is equal to 1.01325 bar, is 101.32 kilopascal. Then dry bulb temperature TdB is 32 degrees centigrade and wet bulb temperature TWB is 26 degrees centigrade. So we need to find the partial pressure of the water vapor. So when dBT and WBT are given, we have to use this Carrier equation which says PV is equal to PVS of WB, that is wet bulb temperature, minus of this P total pressure minus PVS of WBT multiplied by the difference in the dBT and the WBT temperature divided by 1547 minus 1.44 WBT. So now from the steam tables, now open the table and go to this table number 2. Under the table number 2, under the wet bulb temperature of 26 degrees centigrade. So at 26 degrees centigrade, note down the pressure. So that is nothing but the partial pressure of the saturated partial pressure of the vapor. So at the wet bulb temperature, that is 3.36 kilopascals. Now substitute this here. Total pressure we know, this vapor pressure at WBT, substitute and you know WBT temperature and dry bulb temperature. So substitute, we'll get the partial pressure of the vapor, that is PV. Next, to find the specific humidity. So omega is equal to 0.622 PV by PA. So we have just now obtained the PV value divided by the PA is nothing but the partial pressure of the air. It is nothing but the total pressure minus vapor pressure. So substitute, we'll get the specific humidity omega. Next, to find the relative humidity is the ratio of partial pressure of the vapor divided by vapor partial pressure at dBT temperature. Only in the Carrier equation, we have to use the vapor at the WBT temperature. But here we have to use the at dBT. So again, and in the steam tables, in the table 2, at dry bulb temperature of 32 degrees centigrade, find out the pressure. And in substitute here, we'll get the relative humidity as 62.2%. Next is degree of saturation. It is given by mu is equal to PV by PVS into P minus PVS divided by P minus PV. So PV we know 2.97 and PVS. This PVS always generally PVS means it is dry bulb temperature, not the wet bulb temperature. So dry bulb temperature PVS, substitute here. Then P is the total pressure minus vapor pressure, saturated vapor pressure divided by again the P minus vapor pressure. So we'll obtain the degree of saturation as 61.8%. Next, dew point temperature. This dew point temperature is always found out for the, so we have pressure PV, the vapor pressure. So we have to go to the first table, table 1, wherein first column we will have the pressure. So go to the table 1, and in table 1 for the pressure of 2.97, obtain the temperature, saturated temperature, that is nothing but 23.9 dpt. This is the dpt. It is dew point temperature. Dew point temperature is nothing but the saturated temperature. Next, to find the density of the air density, we will assume the ideal gas equation. PAVA is equal to MAR into TA. So for the air, so R is nothing but we already know this, generally it is 287 joules per kg Kelvin, or if we substitute it is 0.287 kilojoules per kg Kelvin. Here PA divided by, so we'll cross multiply, so get MA by VA will be equal to PA divided by R into TA. R value it is 0.287, here it is substituting kilojoules per kg Kelvin, multiply by the air temperature. Make sure whenever you substitute in the ideal gas equation, it should be the temperature should be in Kelvin. So dry bulb temperature in terms of Kelvin. So in the numerator, P means it is total pressure minus PV the vapor pressure, it is 2.97, we'll get it as 1.12 as the density of the air per meter cube of the dry air. Next, we'll find out the density of the vapor. To find the density of vapor, again substitute in the ideal gas equation. In the ideal, whenever we go for ideal gas equation, RV, we have said it should be in, again, get the value of RV. If it is RA, air means it is 287. But here the vapor, substitute to find the vapor gas constant is 8.314 kilojoules per kg Kelvin divided by molecular weight of the vapor means it is nothing but the water. So this taken as 2 into 1 plus 16. So we will get the RV as 0.462. Then temperature, it is dry bulb temperature in terms of Kelvin, and PV vapor pressure. Substitute, we'll get the density of the mass by volume is nothing but the density. So vapor density is obtained as 0.021. Next, to find enthalpy of the air, so we know that H is equal to 1.005 TdB plus omega into this equation. Substitute in this equation, we'll find out the enthalpy of the mixture. Next, we'll go to the next problem. It says a room measures 5 meter by 5 meter by 3 meter. So the volume of the room is 5 by 5 by 3, it is 75 meter cube, which contains the atmospheric air at 100 kilopascal, that is 1 bar. The dry bulb temperature TDB is 30 degrees centigrade and the relative humidity is 0.3. Find the mass of the dry air, MA, and the mass of associated water vapor, MV, in the room, and solve the problem without using the psychrometric chart. So, open the table. In the table, again table 2 having the temperature, also temperature and pressure. First column has temperature. So at dbt 30 degrees centigrade, find the saturated partial pressure of the vapor. So it comes to 4.242 kilopascal. But we know relative humidity is nothing but PV by PVS. So since relative humidity is already given, so PV is nothing but 5 into PVS. So 5 substitute here, multiply by PVS. So we'll get the partial pressure of the vapor. For moist air, we also know total pressure is nothing but air plus pressure of air pressure, dry air pressure plus vapor pressure. So pressure, partial pressure of the dry air will be equal to P minus PV. So we'll get the air partial pressure. Now, so once we get PA and PV, then substitute these two in the ideal gas equation. So PAV is equal to MERDAT. Why V is constant? Because always the gas occupies the volume of the container. So volume remains same, and also the temperature will remain same for both the equations. So MA will be equal to PAV by RAT. Since V is already given, so as volume of the room as 75, we will substitute pressure of the air. We know R for the air it is 287, and temperature it is dry bulb temperature in Kelvin. So substitute will get the mass of the air. Next, to calculate the mass of the vapor, again substitute in the ideal gas equation for the vapor, and then substitute the PV, vapor pressure, total volume remains same. R is again, as we have already seen, it is nothing but for the vapor RV, substitute, then T is the temperature, the dry bulb temperature in Kelvin. So we will obtain the mass of the vapor as 0.682 kg per kg of the air. Mass of the air is, dry air is 85 kgs, but mass of the vapor is just 0.682 kg. So that means the moisture content will be very less. Thank you.